Okay, we're going to lecture here, and then obviously, as you can hear from the conversations, we will examine later on all that stuff. Seems like good questions I'm hearing. All right, so put those together for later. We're here at chapter 15. We got a few more stuff that I think to talk about in there. We've been talking about here in chapter 15 geometry, and we've been talking about really solution stoichiometry. So remember that when we do these type of problems, they really are like regular stoichiometry problems, which means, again, you want to follow those steps that we talked about, which is, again, a balanced equation. We want to convert to moles. We want to make sure that, are we in a limiting reagent type situation or not? Then we want to do the mole to mole relationship. And lastly here, convert those moles to some other unit. So the kind of main difference with solution stoichiometry and really with all stoichiometry problems in terms of if they're not traditional stoichiometry problems where we use grams to moles is usually step 2 or step 4 here. Step 2, in the case of solution stoichiometry, we would use our molarity and also our liters. So remember, molarity is our moles per liter. So our moles would equal liters times our molarity, if I could get that there. So that's a very common sort of use of it in solution stoichiometry. Remember that if you do have enough information given to you for both reactants that you could get to moles, that again means that it is a limiting reagent problem. So you do actually have to do, as I think we've talked about, a calculation to determine if it is limiting reagent or not. You can't just take the smallest number. So there has to be some type of calculation to determine that. If you don't have enough information to get to moles of each of the reactants, then it's just a basic stoichiometry problem. You don't have to worry about the limiting reagent part of it. Once you do, if it is a limiting reagent, you would obviously continue on with that. If it is not a limiting reagent, then you would continue on with what they gave you. And you do the mole-to-mole relationship from the balanced equation. And lastly, at the end, also sort of a variation on these type of problems. You will have moles at this point. So a lot of times you may use the moles and the molarity there to figure out the liters. Or you may actually just use the moles that you calculated and the volume that's given to you to calculate molarity at the end. Or you may just still do moles to grams, use a molar mass at the end. So there's some various ways that these sort of problems end. So we did some last time, bless you. We also talked about when you do titrations, that's really these neutralization reactions, acid and bases, are just stoichiometry problems where, again, that kind of second step and fourth step where we kind of change it up a little bit from grams and molar mass in a lot of cases. Any questions on any up there? All right, so I think we did not do this example because I remember screwing up the previous example. So I think we're on this one. So let's do this one here. In a titration, requires 63.5 milliliters of calcium hydroxide to reach the equivalence point with 95.5 milliliters of hydrobromic acid. What is the molarity of the hydrobromic acids? Okay, so let's take a look, see how you're doing. So obviously we're doing a titration, which definitely is a stoichiometry type problem. So we do need an equation. So remember, when you're going to write the equation, you want to make sure you start with the correct formulas first. So calcium hydroxide, calcium is +2 and hydroxide is -1, which means when you put it together, you should end up with something like this. And we're going to react it with some hydrobromic acid. This is an acid-base reaction, which is basically a double displacement reaction. So our positive guys, once again, are going to swap partners. It's also an acid-base reaction, which means you should know that you get water. And once again, the water obviously comes from here and here. That means the calcium and the bromine will come together Once again, we want to put it together properly. So calcium is +2 and bromine there is -1. So we'll end up with something like this. Once you have all of the formulas there correctly, now is the point to make sure that it is balanced. Again, you do not want to try to do both of that together. Get rid of some of that. So it looks like to balance this guy here, we're going to need some 2s, I think. So maybe we got 2 here and probably a 2 right about there. I think we'll do it. Any questions on the equation there? All right, so now that we have it, let's take a look at what was given to us. We have 63.5 milliliters. We also have the molarity of 0.375. Once again, I'm going to turn that big M into both units, which are our moles per liter. In terms of the hydrobromic acid, we have 95.5 milliliters, and we are looking for the molarity here. So once again, we're looking for the molarity, which means we are looking for moles per liter. We essentially have the liters part of it right there. So we do need to get the moles part from really the stoichiometry. We also know this is not a limiting reagent type situation because we're looking for a reactant. So clearly we don't have the moles of each reactant. So it's just a basic problem. So we can get obviously our moles of our calcium hydroxide from both of this information here. We do again need to make sure that our volume is in liters, so everything properly cancels out. So we want to take our 63.5 milliliters. We're going to convert it into liters by dividing by 1,000. That will get us 0.0635 liters of calcium hydroxide. We now can use our molarity here to go from, again, our liters to moles. And we actually could multiply it by the molarity. And once again, by using the both units there, we could hopefully clearly see where the liters is. The liters here will cancel. If you get an answer at this point, 0.0635 times 0.375, you'll end up with 0.02381. Take it to a couple digits there, more than probably I need, just to make sure. At this point, that's close to what I need, but we need actually the moles there of the acid. So this is the stoichiometry part. So really, right, we've done our kind of first step. We've done our sort of second step here, convert to moles. So now we're going to do our mole-to-mole relationship. So from the equation, we could see that we have 1 mole of calcium hydroxide gives us 2 moles of hydrobromic acid. So that's where we'll continue on here. So using that, we want the moles of calcium hydroxide to cancel. And we're going to have our moles of HBr on top. Moles there will cancel. And at this point there, we're going to multiply it by 2, basically. Going to give us 0.0476 moles of HBr. That's basically our third step, which is our stoichiometry step here. That's important because that really is our missing piece, right, that we need there for our molarity. So we have pretty much everything that we need. We do also need to convert the milliliters of HBr into liters as well, so everything cancels correctly. So we'll do that. We'll take our 95.5 milliliters, once again, divide it by 1,000, move to decimal place 3 places to the left, whichever way you want to do it, I suppose. So now that we have that, we could get the molarity, which would be 0.0476 moles of HBr divided by its liters, 0.0955 liters. And that's going to get us there. Looks like 0.499. And again, the units don't cancel, so you can leave it as moles per liter. R, you can write 0.499 and put the big M back in there, HBr. And obviously this would be our fourth step. Instead of using molar mass to go from moles to grams, here we're going to into the molarity equation. Any questions on any of those steps there? Yeah. So pretty much the center part there is pretty much just like a normal stoichiometry problem. And really here, sort of how to get the moles at the beginning and what we do with the moles at the end is just sort of the difference pretty much in any stoichiometry problem is those two parts. Yeah. Any questions? Okay, so that is solution stoichiometry. Let's talk a little bit about another sort of concentration unit that I don't know, you probably won't come across too much, but we'll talk about, I guess. And that's normality. And normality is not to be confused with molarity. Normality actually has the abbreviation of big N versus big M. Normality is another unit of concentration that is sometimes used, a lot of times dealing with acids or bases. And it deals with really how much, in the case of acids, how much H pluses will come off in those acids, which is what makes something an acid. When you're dealing with bases, which you could do this for as well, it's how much OH minus sort of comes off as well. So one equivalent of an acid is the amount of acid that will give you basically 1 mole of H plus. 2 equivalents of base is basically how many moles of OH you will get in 1 equivalent of base. And sometimes we do calculate what is known as the equivalent weight or equivalent mass, which is grams per equivalent instead of grams per mole. So essentially, for example, if we have something like HCl, when it breaks apart, we do get H plus and Cl minus. And really from this, what you could get is for every 1 mole of H plus, in this case, you get 1 equivalent, basically, is sort of the relationship that you could get from that. If you had something like H2SO4, that will give you 2 hydrogens plus SO4 2 minus. And this would then give you basically for every 1 mole there, you will get 2 equivalents because you get basically 2 hydrogens that come off in this case. So we could kind of use it as a conversion factor to, sort of use a different unit. I would say most of the time people don't use normality all that much anymore. People usually use molarity, but occasionally you'll still see it. I don't know if you remember, but if you looked at like the label that was on, like the sodium hydroxide and like the HCl, it was given in normality. So sometimes, solutions come in normality, and but most of the time we deal with molarity. So let's take a look at some of these things. A reminder that some common acids like HCl, nitric acid, sulfuric acid, these are strong acids. Remember as well things like hydrobromic acid, hydriodic acid, perchloric acid is also, that's kind of like your 6-pack there of strong acids. Sodium hydroxide, potassium hydroxide are strong bases. Once again, kind of hydroxide in things in group 1 or group 2, especially if we go down sodium to potassium, hanging right there to calcium and strontium and barium. Those are all kind of strong bases that are when they have hydroxide in them. So as I showed there on the last slide, if we HCl can only give away basically 1 H plus is what's referred to as being monoprotic. It has 1 proton to give. That means 1 mole of HCl is equivalent to 1 equivalent of HCl. So that means the molar mass will basically be the same as the equivalent weight because it's basically a 1-to-1 relationship. So if we did, for example, HCl, that is 1.008 grams per mole plus 45 grams per mole. And if we add that together there, that's going to give us our molar mass. And that'll give us 3646. Once again, that's our molar mass. And if we look at this relationship, we could do sort of a relationship here between our moles and equivalent. What we see is basically 1 mole of HCl will give us 1 equivalent. So the moles of HCl will cancel, and you'll end up with 36.46 grams per equivalent. And that is the equivalent mass, which is the same in this case as the molar mass, because it's basically a 1-to-1 relationship between them. So sometimes on monoprotic acids, the equivalent mass and the molar mass will be the same because it is a 1-to-1 relationship. Obviously, if it's not a 1-to-1 relationship, the equivalent weight can be different than the molar mass. Any questions on that there? So let's take a look at one here. We want to figure out the equivalent weight in grams per equivalent for H3ASO4. So the first thing we could do is calculate the molar mass from the periodic table. So if we do the molar mass here, that is 3 times our hydrogen from the periodic table. We'll look up AS, which is not used all that much. 7692, I think is what that says. Go with that. Maybe 7492. That is 7492 for AS, and 4 times 16 there for our oxygen. So that's going to give us 3 times 1.008 plus 74.92 plus 4 times 16. That will again give us here a molar mass of 141.9 grams per mole. When we look at this acid, this is a triprotic acid, which means when it breaks apart, you're going to get 3 hydrogens to come off here. And we'll have something like this. That means that basically in 1 mole of H3ASO4, there will be 3 equivalents. Basically because there's 3 hydrogens that's coming off in this particular case. So we would use that as a conversion factor, and we would have 1 mole is 3 equivalents. The moles will cancel. So basically we divide it by 3. We end up with 47.31 grams per equivalent. So that would be our equivalent weight in this case. Any questions on that? So in this case, obviously the equivalent weight and the molar mass are different because obviously you get basically 3 equivalents per 1 there. Any questions on that there? Now, normality, which I said before, is very kind of similar to, in a sense, molarity, but it is the number of equivalents per liter. So it's not how many moles per liter like molarity is, it's the equivalents per liter, which again are essentially related to how many H pluses will come off or how many OH minuses will come off in that case. And again, when we look at molarity, which is moles per liter, really to go between the two, again, is that relationship of how many H pluses or so to come off, basically, that will allow you to do that. So let's take a look at this example. We have 2.5 molar H2SO4. What is the normality? So when we look at this, this is 2.5 moles of H2SO4 per liter. And we want to end up with normality, which is the number of equivalents per liter. So really the bottom part here is the same. So we need to look at our H2SO4, and as we talked about earlier, we will get 2 hydrogens that come off. in this case. And that means basically 1 mole of H2SO4 will give us 2 equivalents. And in this case, we will use as a conversion factor to go from molarity to normality. So 2.5 moles of H2SO4 per liter. 1 mole of H2SO4 is 2 equivalents of H plus, basically. So the moles will cancel, and that will give us a normality here. If I don't times it by the right number, that would be better there. 5 equivalents per liter, which is 5 for the normality. So just like molarity, you could use big N at the end, just like you use big M for the unit, or you could leave it in equivalents per liter. So the normality here of this solution is actually twice the molarity, again, because of the 2 hydrogens that are coming off. Which means obviously if you want to go back the other way from normality to molarity, you would in this case divide by 2, right? It would take you backwards to the molarity. Any questions on normality here? Okay. So why don't you give this a try? So hydrogen is 1.008, phosphorus is 3097, and we got their oxygen is 16. So we have a solution of phosphoric acid as 50 grams of phosphoric acid per liter of solution. Okay, so let's take a look. In this case, we have a solution of phosphoric acid, which is H3PO4. Again, it's going to break apart into 3 hydrogens and a phosphate. That would mean really that 1 mole of it will give you basically 3 equivalents of H plus from there. And in that relationship here, we basically have how many grams there are per liter. And we really want to get to normality, which is equivalents per liter. So really, to get there, we kind of have to go from grams to liter, perhaps to molarity, moles per liter, to normality, which will take us from equivalents to liter. So the first thing we probably want to do is figure out the molar mass so that we can get to really the molarity of the solution. So once again, to get the molar mass, we'll take 3 times 1.008 for our hydrogen, plus our 3097 there for our phosphorus, plus 4 times 16 for our oxygen. That's going to give us a molar mass here of like 9799 grams per mole. We'll use that as a conversion factor here. We actually want the grams on the bottom so that they cancel. The grams here will cancel. Once again, if we stop right at this point, we basically have the molarity of the solution, right? Moles per liter. We need to go one more step there to our normality. So again, that's where the relationship of basically how many hydrogens are going to come off here is going to work. So we're going to use that as a conversion factor to kind of take it the rest of the way. We'll go with 1 mole is our 3 equivalents in this case. The moles here will cancel. Now we're left with our normality, which is our equivalents per liter. And this would then be something like 1.53. And again, you could leave it as equivalents per liter or 1.53 and just write a big N. Again, kind of like what you do with molarity in this case. Any questions on normality? My guess is you'll barely see it ever. Yes, but occasionally maybe titrations in the next class. Maybe they'll see it a little bit there, but not too much used in most cases. Any questions on any of that stuff there? All right, that's your wrap chapter 15. So we're going to continue on for just a bit here. So chapter 14, not too long of a chapter. So we're going to cover some stuff that we kind of talked about as we've gone through some of the other chapters. This will also tie back to some of the stuff we did earlier on when we did stuff like specific heat in that earlier chapter, I think, with the energy. So that will come back in here. We'll also talk about how, again, officially molecules interact with one another through intermolecular forces. So we're going to first start with water and its phases. And we're going to talk a lot about what happens when we kind of change phases of substances and go from, say, solid to liquid, liquid to gas, and so forth. Pure water obviously is colorless, tasteless. Its normal freezing point or melting point is 0 degrees Celsius. A reminder that as you go from solid to liquid or liquid to solid, that is where that occurs. And it occurs exactly at that same temperature. So as you go from, say, solid to liquid and do the process of melting, or you go from liquid back to solid and do the process of freezing, they do occur at the exact same temperature. And for the case of water, that's 0 degrees Celsius where that occurs. As we've talked about before, and as we'll talk a little bit more about here again in this chapter, it's not really until you sort of get a little bit above 0 degrees Celsius that you do sort of transition into liquid water, and not until you get a little bit below 0 degrees that you really sort of, in the case of water, transition to ice. You again sort of have right at 0 degrees, sort of like ice crystals, a little bit of both phases happening. It's what's said to be the two phases are in equilibrium with each other. So you got both things happening at basically the same time. That's also the same sort of situation that occurs when we get, for example, for water at its normal boiling point, which is 100 degrees Celsius. And at that boiling point, or a substance's normal boiling point, that's where we have our transition from liquid to gas, or going backwards, obviously, gas back to liquid, which is the process of condensation. That also occurs at the exact same temperature and exactly at 100 degrees. You again have really both phases sort of happening at the same time. A little bit in that case of some steam, and you got a little bit of, say, liquid water sort of happening at that point. What determines really sort of which way you go is really the energy component, as we might have talked about earlier on. If you continue to put energy in, which is an endothermic process, you will continue to go, for example, from solid to liquid to gas. Those are all endothermic processes. And remember that when you have an endothermic sort of value for energy, it is usually a positive number. So I think we talked about some different units of energy. For example, delta H is a positive value. Delta H is the change in enthalpy, if you remember. And as we continue to do that from solid to liquid to gas, everybody's gaining more energy, which means they will have enough energy to really start working their way up on another. Obviously, in the solid state, as they gain energy, they have enough room to start moving past one another, which is why it goes from solid to liquid state. And as you go from liquid to gas, they have enough energy to completely break apart from one another and their intermolecular forces, as we'll talk about more in this chapter, to go from the liquid state to the gas. Obviously, if we're going in the reverse sort of directions, going from gas to liquid to solid, those are all processes, again, that need to release energy to do so. And that is exothermic processes, where we will release energy. And again, when you have energy values that basically represent an exothermic process, they are typically negative values. And the same idea there, our delta H would be typically a negative value for that. So when we go from 0 to 100 degrees Celsius, that is all liquid water in that point until we get to those transitions. Water does expand when it freezes, and water is an unusual sort of substance in that sense because of the really strong hydrogen bonding that happens between different water molecules, as we'll talk about. So when we have water molecules that come together, water, which is a polar molecule, has a negative side, which is the oxygen side, hydrogen, really the more positive side. They're able to do what is referred to as hydrogen bonding with each other. And that is a pretty strong sort of interaction. But what happens in the case of water is as they kind of go into the solid phase, because of this really sort of strong attractive forces, they actually end up, as they sort of bond together, my really bad drawing of circles here, basically, as they bond in the solid part, they actually end up creating a lot of empty space between the different ones. Unlike normal substances or most substances, when they kind of relax into the solid state, they're able to really sort of pack in there pretty tight to one another. They're able to get pretty densely populated with each other. In the case here of water, because of that strong hydrogen bonding attraction, what ends up happening is they can't really get so close to another, and they create all this open space. And that affects properties of water that are different than other substances. As you know, hopefully, right, that the solid version of water, which is ice, is actually less dense than the liquid version. And that's why our ice cubes float, right? In our drinks, when we put it in there, they float to the top. And that's because of this big empty spot that happens. If we think about the density formula, which is D is equal to M divided by V, because it creates all these big open spaces between the different water molecules, what you're essentially doing is increasing the volume. And as that number gets larger on the bottom, obviously, if you divide something by a larger number, the density actually goes down. And that's why we see that the density of ice is actually less than liquid water. So typically, liquid water's density is 1 gram per milliliter. The density of ice, for example, is 0.917, which things that are less dense than each other, right? The less dense guy will sort of float, for example. The more dense will sort of sink in that case. Any questions there? So this is a heating and cooling curve as we go from, for example, the 3 sort of states of water. We have our ice, which is obviously our solid version. We have our liquid water here in this area, and we have our steam, which is basically our gas version here of water. So we do have these different sort of transitions that occur, and it is energy related in terms of as we take a substance from one phase to the next, there is a certain amount of energy required to do solely just that, not change the temperature or anything like that. But there's a certain amount of energy just to take this guy at, say, 0 degrees Celsius to 0 degrees Celsius solid to 0 degrees Celsius liquid, not change the temperature, just change the phase. And when we look at those things are a couple of things, and these are specific here for water. That is the molar heat of fusion. So the heat of fusion, which is 6.02 kilojoules per mole for water, that's roughly 335 joules per gram. That is the energy that's required to take a substance from solid to liquid and liquid back to solid. And for water here, that occurs at 0 degrees Celsius is where that occurs. And it is a positive number, and this is what is sometimes referred to as the delta H of fusion. And the delta H of fusion is the energy required to do that. So as we were just talking about, going from solid to liquid is a endothermic process, which means if you were doing that process, the delta H value would be positive. If we use this value here, 6.02 kilojoules per mole, are positive about 335 joules per gram. Now, if we were going in the other direction, going from liquid back to solid, which is the process of freezing, it would be an exothermic process. The amount of energy is still the same, but the sign would be different. So the delta H going in the opposite direction, liquid to solid, delta H here would be negative 6.02 kilojoules per mole, or negative 335 joules per gram. So the energy is the same, but the sign is different to indicate, again, as we talked about when we did the energy chapter, it's really important to keep the proper sign when you are doing any type of energy calculation, again, because it tells you whether or not it's an exothermic process or an endothermic process that's basically occurring. And the same thing happens at the normal boiling point. So the value that we see here is for water, and that is 40.6 kilojoules per mole, or roughly 2260 joules per gram. And that is the heat of vaporization, or the delta H of vaporization, it is sometimes called. And that is also what happens as we go from liquid to gas, or gas back to liquid. And in the case of water, that is 100 degrees Celsius where that occurs, which is a normal boiling point. So going from liquid to gas, which is an endothermic process, the delta H would be positive 40.6 kilojoules per mole, or positive 2260 joules per gram. Going from gas to liquid is exothermic, so the delta H here would be negative 40.6 kilojoules per mole, or negative 2260 joules per gram, going in that direction. We also see here that just from the numbers and the example here of water, it takes a lot more energy to do the transition of going from liquid to gas than it does going from solid to liquid. So again, going from solid to liquid in the case of water is like 335 joules. To go from liquid to gas is like 2260 joules. So quite the jump in energy. And that's related to what happens as we do those transitions. It is much easier to take something in terms of energy from solid to liquid, because as it goes from solid to liquid, in the solid state, everybody's pretty close to one another. In the liquid state, they're still relatively close to one another, all the molecules, but there's a lot more room for movement and passing, which is why they're fluid. But when we do that transition of going from liquids to gas, at that point, you need to completely break apart everybody from one another. And that's going to require a lot more energy to overcome those intermolecular forces, allow those guys to jump into the gas phase. So we always see a much higher value for the delta H of vaporization, or the heat of vaporization, than we do for the heat of fusion, because it just requires a lot more energy to break everybody apart, and also requires a lot more energy for everybody to lose to come back into the liquids phase, as they're flying around really fast with a lot of energy in the gas phase to go through condensation. Any questions on that? Now, this energy is only the energy that's required to do nothing more than change the phase. So the temperature here actually stays the same, but the phase of the substance changes. And that's different than if we wanted to calculate something like the energy required to change the temperature of something, but keep it the same phase. And that calculation is something that we did earlier on, and that is the specific heat calculation. So if you remember when we talked about specific heat, that is our Q is equal to ms delta T, right? That's our heat or energy. That's our mass. That's our change in temperature, which should be our final minus our initial. This is our specific heat capacity, which has those 3 units of joules per gram per degree Celsius, are calories per gram per degree Celsius. Remember that liquid water is that number, right, that you're supposed to know, 4.184 joules per gram per degree Celsius, are 1 calorie per gram per degree Celsius. We also maybe talked about it as well, but if it is not liquid water, then the specific heat capacity will not be that number. Again, if it's something like ice, which is also water, or if it's something like steam, which is also water, the specific heat capacity is like 2 versus 4. So it's important, if you go to those tables, or a table of specific heat capacity, that you find the substance you're looking for and the correct phase, because they will be perhaps different numbers, and water obviously is a big sort of factor. But most of the time we do liquid water, and that is the number we use. We did it when we heated up, right, those big test tubes with all the metal, and we dumped it into the coffee cups and all that kind of experiment that we did. So when do we use all these things, and how do we use all these things? Well, we use these things if we want to know how much energy is required to change a substance from one phase to the next. So if you're doing any type of phase transition, which means that you're keeping the temperature the same but changing the phase, then you want to use these guys here for that. So basically, same temperature, different phases. Now, if you're doing the same phase but different temperature, then it's a specific heat calculation. So if you're doing some type of same phase but different temperatures, then it's a specific heat calculation. One of the things that's important about energy is, if you remember, it is a state function, which means that you can figure out how much energy it requires to do certain steps along the way. And if you want the total amount of energy, you basically could just add them all together and you can get the overall energy that occurs. Any questions on that? So if we were to look, for example, at this heating and cooling curve here, just to illustrate things, this right here is our transition between solid and liquid. And that's exactly at 0 degrees Celsius, which is where water that happens. That is a situation where you would use your delta H of fusion, because that's the energy required to do that change. Over here, which is 100 degrees Celsius, also a flat line before I scribbled all over it there, is the transition between liquid water and basically gas. And that would be our delta H of vaporization. They are flat line because the temperature again remains constant when you do these processes. You could also see from this graph, it is a much longer line there, right? As you go from liquid to steam, as opposed to ice to liquid water, again, requiring more energy to do so. Now, what would happen if we were not at a flat point on this curve? You know, a point like this, or any point kind of coming this way, or coming this way. All of those ones that I just colored in blue are situations where the things remain the same phase. So down here, all through here, that is all solid. All through this blue part is all liquid. And all through this blue part is all gas through there. So if we're at any point in any of those blue lines where you're kind of moving upwards or even down, you're in the same phase, but you are changing the temperature. So those would be points where you would use the specific heat equation to figure out how much energy is required to do that. So in these parts of the graph, that is your Q is equal to ms delta T. And like I said, if we were taking something from, say, ice all the way up, we could just do calculations for each of the steps along the way, add up the total energy. Any questions? So this is a heating curve as go from ice upwards, as you can see here, and it's a cooling curve as you come this way. The only real difference as you're traveling up, or if you're traveling down, is what's happening with the energy, right? So again, if you're starting at the bottom there from ice going to gas, that's all going to be endothermic processes, which means when you calculate the energy or the heat for all those processes, as you go from solid to liquid to gas, you should end up with positive numbers all the way through. And going backwards, the only difference is it's exothermic. So everybody's releasing that energy, which again means that you calculate the energy for all those spots, negative numbers. The numbers will be the exact same numbers, no matter which way you go. The only difference again would be the sign, and that's that conservation of energy, right? So whatever is lost should be the same amount of energy that is gained. Any questions on that? Now, when we talk about 0 degrees Celsius and we talk about, go this way. When we talk about 0 degrees Celsius and we talk about this sort of heat of fusion, delta H of fusion and delta H of vaporization, these numbers are specific for water here. And obviously the boiling point and melting points and freezing points of 0 and 100 are specific for water. If you're dealing with some other substance, they will have a different value for delta H of fusion and delta H of vaporization, and they probably will have a different boiling point and melting point temperature as well. But most of the time, probably water is a lot of times what you deal with. But just keep that in mind. You know, if you see some different numbers for different substances, that's because they are different than water. So these numbers are specific for water. So let's take a look at an example of how we would do this. Let's say we wanted to know how much energy is required to change ice at, that's actually, I think, minus 3.5 degrees Celsius. The negative there's at the end, to steam at 102 degrees Celsius. So when we do these calculations, we're just going to do it basically step by step. So let's take a look at where we are, and we could use sort of the graph here to help us. So the very first part is I'm going to be starting somewhere in this ballpark down here at -3. So the first thing that would happen is I would need to take that ice at -3 degrees Celsius up to ice at 0 degrees Celsius, right at the point where we might transition. So we're not going to transition yet, but I do need to take it. Basically, my very first step is to take it from that -3.5 to 0 degrees Celsius. So in this case, the very first thing that we would do is take the ice from -3.5 degrees Celsius to ice at 0 degrees Celsius. So this is basically the same phase, but we're changing the temperature. So this is going to be a specific heat calculation. So this is going to be Q is equal to ms delta T. Here our initial temperature is -3.5 degrees Celsius. Our final temperature is 0 degrees Celsius. And we have our mass. We don't have our mass, so let's just make a mass apparently. How much energy is required to change? Let's go with 125 grams of ice. That would be a good number to probably have. We'll add that in there. So we do have the mass now given to us, 125 grams. And we do need the specific heat capacity. So if we were to look up the specific heat capacity, again, we would not use the 4.184 number here because this is not liquid water at this point, right? It is ice. So we would want to use the specific heat capacity for ice, which is approximately, we'll go with 2 joules per gram per degree Celsius. So the specific heat capacity for ice, again, different than for water, and we would want to use the correct one here. Give or take there a digit, I think, for our ice. So we have everything that we need. So we could calculate this. Q would equal our mass, which is 125 grams, our specific heat capacity here of our ice and not liquid water. Remember, we do want to take final minus initial here. So that's going to be 0 minus a -3.5 degrees Celsius. And that's going to yield us here. And we'll go with 125 times 2 times 3.5, basically. About 875 joules of energy, as those guys will cancel. And that is the energy really to do the very first step of sort of our transition. At this point, if we look at sort of where we're at on our graph, we are sitting right there at 0 degrees Celsius, which is the normal melting point for water. So we have to actually do a phase change at this point. So the second thing that would happen is we would actually take it from 0 degrees ice to 0 degrees liquid water. So that's going to be our phase change that's going to happen. And that's going to require the delta H of fusion. This is the same temperature, but we're changing the phase. So that is where we would use something like the delta H of fusion. So if we do that here, the second step would be taking it now from 0 degrees Celsius of ice to 0 degrees Celsius of liquid water. So that's going to be our delta H of fusion. And I'm going to use the 335 joules per gram version that we talked about. So in this case, we're not changing the temperature, so we're not going to use the specific heat equation. All we have to do is take our mass, which is 125 grams. We're going to times it by the heat of fusion, which is our 335 joules per gram. Grams will cancel, and that will get us 125 times 335. Give us approximately 41875 joules, or if we want to round a little bit here, 41841, actually 9 we'll go with. joules of energy in this case. So that is the amount of energy that is required to change the phase of that thing from solid to liquid. Any questions so far? So if we see where we're at this point, we are now sitting right about there. So the next thing that needs to happen is we actually need to now take it from liquid water, as we just did the phase transition, all the way up. You're right about there. And that would be the third step there. And that is liquid water all the way across there. And we have the same phase all the way across, but we are changing the temperature basically from 0 to 100 degrees. So once again, to figure out the energy, we would have to go back to our specific heat equation at this point. And the third step here then would be, we're going to take it from 0 degrees Celsius liquid water to 100 degrees Celsius liquid water. And that again means that we do have to go back to our Q equals ms delta T. In this case, our final temperature will be 100 degrees Celsius. Our initial temperature will be 0 degrees Celsius. We will still have the same mass. But now that we are in the liquid water region, our specific heat capacity is the 4.184 number. Again, because now we're actually are in liquid water. So we're going to put this into this equation. So Q will equal 125, the 4.184 joules per gram per degree Celsius. Once again, taking final temperature, which is 100, minus initial temperature. And that's going to get us here 125 times 4.184 times 100, basically. And that will get us 52300 joules. So that is the energy required basically to take us from 0 degrees Celsius to 100 degrees Celsius in terms of liquid water. Any questions on that? So again, here we had to adjust our specific heat capacity because we're now in liquid water. So we want to make sure we don't use the 2 here. We actually use, again, the 4.184. So we're almost there. We want to get to 102 degrees. So we're very close to that. If we take a look at our sort of chart as to where we are sitting. So at this point, we are sitting right about there. So the next thing that has to happen at this point is we're sitting at 100 degrees liquid water. We need to take that liquid water to basically steam or gas at 100 degrees. So we have to do another phase change because we're sitting at the normal boiling point here for water, which is 100 degrees Celsius. So the next thing that will happen is we will do this transition right there. And that again is going to be the delta H of vaporization as we go from liquid to gas in this case. So if we add that to our growing list here of calculations, we're going to fourth step, take it from 100 degrees Celsius liquid water to 100 degrees Celsius steam, which is gas. And that's going to require the delta H of vaporization. And I'm going to use the joule number. So that's 2260 joules per gram, again, specifically for water here. So we're just going to multiply basically the mass of our water, which is 125 grams. Obviously, you will not change the mass because hopefully you don't spill anything along the way. So it should all be the same thing all the way through. 2260 joules per gram. Those are going to cancel. And that will get us 125 times 2260. Get us something like, we'll go with 283. I'll do a little rounding there. 123 joules. So we have that number right there. And that is about 283,000 joules to convert it from liquid into gas. Just as a note for comparison purposes, it only took 41,000 joules to take it from solid to liquid. So again, takes a lot more energy to go from liquid to gas than it does to go from solid to liquid, because again, we have to fully break things apart. We're almost there. We are now sitting at 100 degrees steam. The last thing is just to take it up here to 102 degrees Celsius. So the very last step there, I'll just do it on the next page, is to take us from 100 degrees Celsius steam to 100 degrees Celsius, 102 degrees Celsius steam. So this once again is the same phase all the way through, but we are changing the temperature. So back to the specific heat equation. Our final temperature here, 102 degrees Celsius. Our initial temperature, 100 degrees Celsius for this step. Our mass is still the 125. Once again, though, we do need to make sure that we are using the specific heat capacity for steam and not liquid water. So here you would not want to use the 4.184. I'm going to go with 2.03. And I'll be frankly honest, I might have got those reversed, but we'll go with it. Joules per gram per degree Celsius. You can never remember if ice is the 2 and steam is the 2.03 or the reverse. They're quite close. They're both about 2, ice and steam. So we do want to make sure we use the correct value there, which is a 2-ish for both of them. And we'll go into here. We'll go with Q is equal to our 125 grams. We'll use our specific heat capacity there for steam. And again, we want to go final minus initial, which is 102 in this case, minus 100 degrees Celsius. And that's going to give us 125 times 2.0 times basically 2 there as we subtract that. And that's going to get us about 508 joules required to do that step. So what we calculate in each of these individual steps are basically the energy to do the individual steps. Once again, the total amount of energy to take us from here all the way to here is basically adding all of those individual steps together. So the total amount of energy would equal, in this case, step 1 plus step 2 plus step 3 plus step 4 and step 5's energy values. So let us do that here to finish it out. So step 1. So step 1 there was, I think, 8. What we had there? 875. Step number 2 was 41,900. Step number 3 there, it was 52,300. Step number 4 there was 283,000. And obviously here, step number 5, 508. So adding all those together gets us 875 plus 41900 plus 52,300 plus 283,000 plus 508. Going to get us about 378,583 joules. And usually delta H, which is kind of what this is in kilojoules. So roughly 379 kilojoules of energy is required to do this. We are going in this example from solid to liquid to gas. That is all endothermic processes, which means we did end up with positive numbers all the way through and a positive energy. If I were to start in this example at the steam at 102 degrees and work my way backwards to the minus 3.5 degrees ice, what is the only difference in all those numbers? They all will just end up being negative because your change in temperatures would flip and the signs would change. So you would have negative for all 5 of those values, and that would end up being the exact same value at the end that would be negative as well. Any questions on heat of fusion, heat of vaporization, phase changes, how it ties into specific heat that we talked about earlier? All right, it's a good stopping place, I think.